Hello, my name is Ollie Yakimow, and my mentor is Dr. Scott Franklin. This summer, I was studying a specific type of granular material called a SeSP and how it moves within a system of monodisperse disks. Granular materials are made up of many small solid particles. Unlike other mediums, granular materials characteristically change behavior in response to outside forces. For example, a pile of sand can be packed into a solid shape like a sandcastle, or can be poured like a fluid. We study the behavior of granular materials because it is important to industries such as pharmaceutical and agricultural industries. Common problems in those industries include jamming, which is when particles come too tightly together and stop flowing, and entanglement, which is when particles become linked together. By studying these materials, we can learn what causes jamming and entanglement and learn how to prevent both from happening. In this project, we focus on superellipsoidal sector particles, also known as SeSPs. Superellipsoids are part of a family of closed, two-dimensional curves, commonly known as Lemay curves, which allow for precise control of corner sharpness, aspect ratio, and curvature. They represent a generalized form of an ellipse which is able to be deformed, stretched, and pinched to form corners. Superellipse curves are the set of points to satisfy equation 1. In this equation, parameters A and B function like semi-major and semi-minor axes, and they control the aspect ratio of the curve. Parameters m and n are the degrees of the superellipse and tune the curvature. For this project, we used a laser cutter to cut particles from acrylic sheets. The particles were then placed in a plexiglass annulus whose dimensions are shown in Figure 1. This annulus allows for a two-dimensional movement with minimal friction against the glass. In order to move the particles, we have to generate a horizontal force called shear. This is achieved by rotating via motor the toothed ring that sits on top of the particles, shown better in the inset of Figure 1. The printed ring on the bottom of the annulus is there to prevent the particles from sliding when placed under shear. We take data on the system using a set of 6 cameras, shown in Figure 2. These cameras are evenly spaced around the annulus such that we are able to take images from any point around the system. Our data for this project focuses on video taken from one of these cameras. Our system is comprised of a monodisperse, or single-sized sea of round particles, with a few SeSPs inserted throughout. These particles are marked with a red dot. The round particles have one red dot located at their center, and the SeSPs have 2 red dots, one big and one small. The dots of the round particles are slightly larger than the big dot of the SeSP, which can allow us to differentiate them by size, if we so desire. My project focuses specifically on the behavior of the SeSPs within this sea of round particles. If you'd like to hear more about how the behavior of the round particles is impacted by the presence of the SeSP, check out my colleague Jack Ryan's talk. To take data from the system, I recorded video from one of the 6 cameras, shown here. As you can see, the particles are being moved from right to left across the screen, with the big dots of the round particles showing up here, and the 2 dots of the SeSP showing up there. To analyze this video, I used Interactive Data Language, or IDL, which is a coding program and language that is useful for image analysis. To track the particles, we used IDL programs written by Eric Weeks, David Grier, and John Crocker to identify each particle in the video's field of view and track them. Since the video was recorded on a cylindrical surface, Jack and I developed an IDL program to flatten the images so that we could consistently track particle movements across the entire frame of view. This flattening was achieved by interpolating the coordinates of the video on the curved surface onto a flat rectangle. As you can see in Figure 3, there's this warping around the edges on the left and right edges of the frames, which can make it difficult to consistently track particles as they are not always on the same plane. In Figure 4, however, we have flattened this image, which makes it much easier to track particles consistently as they move from right to left. In order to use the tracking programs, we carefully tested different parameters, such as the separation distance between particles and apparent brightness. Once we found parameters that best fit our data, we were able to begin analyzing. In order to analyze the motion of the SeSP, we need to pay attention to several details. To properly track how the SeSP is moving translationally and rotationally, we use parameters that are known thanks to the tracking program to find more useful information. The track data can provide the position of the SeSP, big dot and little dot. As shown in figure 5, we can see the direction vector pointing from the big dot to the little dot D, as shown here in blue. Since the big dot is in the center of the SeSP curve, we can use it to find the direction in which the SeSP is rotated, shown here in red as n vector. We know that n vector is perpendicular to d vector, so after normalizing both to get unit vectors n hat and d hat, we are able to calculate the coordinates of the center of the SeSP, shown here in an X. We can also overlay this math on top of a frame from a video. As shown in figure 6, we see the math on the previous slide on an actual image with the SeSP. As you can see, the cyan arrow represents d hat, the magenta arrow represents n hat, and the yellow dot represents the center coordinates. And we see how it curves, and they're all a distance from the center. Using this math, we are able to generate an array in IDL that holds the x and y coordinates of the center, the frame number, and the angle. This array allows us to graph how the SeSP is changing position and angle over time. Before we look at an example of one of these graphs, here's what the original video section looks like. As you can see, we have inverted the video so that the particle dots are the brightest points on the image, and we can see each particle being shoved from right to left. Now here's the same video with the track data overlaid on top. As you can see, each particle has been selected, and while there is some background noise, for the most part, it consistently tracks each particle. As you can see, the big dot and the little dot of the SeSP are both highlighted in the circles. Finally, here's the same video with a calculated center of the SeSP overlaid as the empty white circle. And if we picture our SeSP geometry, it makes complete sense and is not just a complete dot floating in space. It would fit right in that center of the SeSP. Now, in our figures here, we see the array of values for frames 128 to 153 of the video in figure 8. In the first column, we have our x position of the center, we have our y position of the center, and we have our frame number. Now we have our graph of the SeSP position and while it moves in 2D motion. So the blue circle shows where it starts at the beginning of the frame set, and the red circle shows where it ends. And as we can see, it travels from right to left, and it matches the values in this array. We can also look at the angular motion of the SeSP. Here we see how the angle of the SeSP changed over that same group of frames. As shown in previous figures, the angle is measured from the horizontal, and for these frames, it would appear that the SeSP hovers between 0 and pi/4 radians. This summer, I was able to capture video from our camera system. While this may not seem like a big deal, our previous program that captured our images was corrupted just before summer term began, and I had to find a new way to take images so that we could take our data. Jack and I also, as shared previously, devised a program to flatten our videos and images from the cameras. This made it much easier to track and identify particles in IDL. I was also able to calculate the coordinates of the center of the SeSP, both by hand and in IDL. I then coded this math in IDL and analyzed a small set of frames. For those frames, I looked at translational and angular motion of the SeSP as it traveled through the round particles. The next step in this project is to begin analyzing other frame sets of the larger video using the same SeSP math I used on frames 128 to 153. Following that, we plan to analyze the mean squared displacements, which is the average motion over time, of the SeSP's horizontal motion, vertical motion, and angular motion. We also plan to set up our cameras so that we can record from all 6 at the same time. This will allow us to take longer and smoother videos that don't have the issues of particles dropping out of frame, and will allow for better analysis of the factors of our system, such as our SeSPs and the round C. Thank you for your time. If you'd like to learn more about the background particles, I would suggest checking out my colleague Jack's talk, which gives a different perspective on this system of granular material.